the diagonalization using similar transformation. I am Associate Professor in Mathematics from PSN College of Engineering and Technology. In our before section, we just see about the matrix calculations, Cayley-Hamilton theorem and etc. In this section, we are going to calculate the diagonalization by using the similar transformation. First, before entering into the topic, we just go into what are the contents I am going to cover in this section. First one is similar transformation, next diagonalization process, next application, where we are using this diagonalization process, and some examples, some practical problems and some MCQs. First one, the definition for similar transformation. Let us recall the definition of the similar matrices first of all. The two matrices said to be similar if there exists a non-similar matrix P such that P inverse AP is equal to B. Then we say that the two matrices A and B are said to be similar. This transformation A into B is known as similar, and we recall the properties of that eigenvalues and eigenvectors that similar matrices have the same eigenvalues. We will use this similar transformation to diagonalize a square matrix. Next definition for diagonalization. For diagonalization, we just go through one theorem. Let us consider the square matrix of order n by n with linearly independent eigenvectors of n is similar to a diagonal matrix D whose diagonal elements are nothing but the eigenvalues of the given matrix A. Means for a square matrix A having n linear independent eigenvectors is similar to a diagonal having the diagonal elements as the eigenvalues. We will prove the theorem by considering. Let us consider the result for n equal to 3. Let A be a square matrix of order 3. Of order 3 means it should contain at least 3 eigenvalues. Let us consider the eigenvalues as lambda 1, lambda 2 and lambda 3. And let us consider the corresponding eigenvectors as capital X1, X2 and X3. Where X1 contains X1, Y1, Z1 and X2, Y2, Z2, X3, Y3, Z3. Now let us calculate the matrix P. P is nothing but X1, X2, X3. I am combining all the eigenvectors of eigenvalues. Where P is a square matrix whose column elements are nothing but eigenvectors. Now consider AP. A into P. A into X1, AX2, AX3, which is nothing but lambda 1 X1, lambda 2 X2, lambda 3 X3. On multiplying this, we just having this X1, X2, X3 into lambda 1 into 0, etc., which is nothing but P into D, where D is nothing but the diagonal matrix whose diagonal elements are nothing but the eigenvalues of the given matrix. Okay. Thus, pre-multiplying by P inverse, we just get P inverse AP equal to D. There we getting AP is equal to PD. On multiplying P inverse by P inverse, we just get P inverse AP is equal to D. Thus, we can transform our matrix A into a diagonal matrix D using a similar transformation. The matrix P, which diagonalizes the given matrix, is also called as a modal matrix of the given matrix A. We have to note one thing, that not for all the square matrices are diagonalizable. Suppose a square matrix A of size n has a less than n linearly independent eigenvectors, then A cannot be diagonalizable. For example, let us consider the matrix A is equal to 1, 2, 0, 2, 1, minus 1, 2, 2 is of size 3. The eigenvalues of this given matrix A is nothing but 1, 2, 2. Now we have to calculate the eigenvector for the eigenvalues. For lambda equal to 1, we have the eigenvector as minus 1, 1. And for lambda equal to 2, we have this thing. This is the only linear independent eigenvectors corresponding to the repeated eigenvalue of lambda equal to 2. Therefore, in this case, we are able to find only 2 linearly independent eigenvectors in total. Since we do not have a 3 linearly independent eigenvectors, the given matrix A cannot be diagonalizable. Next section. We just enter into the application. Why we are using the diagonalizable? Because its major application is, in order to find the higher power of a given matrix, no need to find the matrix multiplication ordinary. Instead of that, we can calculate the diagonalization. Using this diagonalization concept, we can easily find the higher powers. Let us consider. Let A be a square matrix which is diagonalizable. We are taking the matrix which is diagonalizable. Let P be a non-singular matrix such that P inverse AP is equal to D. Then on squaring on both the sides, we have P inverse AP the whole square is equal to D square. P inverse A into, we are calculating twice, so P inverse AP into P inverse AP is equal to D square. On combining these two, P and P inverse gets to 1. So we have P inverse A square into P is equal to D square. Similarly, we can find out on cube both sides, we just get P inverse A cube into P equal to D cube. Instead, on going in the same way in general, we just mentioned P inverse A power m into P can be calculated as D power m. Therefore, A power m is nothing but P into D power m into P inverse, where D power m is nothing but the diagonal matrix having the diagonal elements of eigenvalues of the matrix A. So, it is easy to calculate our D power m. Instead of finding A power m, the value of D power m is very much easy. Then we can find A power m, which is equal to P into D power m into P inverse. This implies as that involving the diagonalization process by less computation, we can calculate the higher powers of the given matrix by directly. For that example, we just go for an example. Problem number 1. The matrix A has a distinct eigenvalues. I am choosing the distinct eigenvalue matrix. Okay. Let us consider the matrix A equal to 1, 6, 1, 1, 2, 0, 0, 0, 3 to be diagonal form. Okay. Hence, calculate A power 8. We are going to calculate the P, which convert the matrix to diagonal form and also find the value of higher power A power 8. Instead of multiplying this A into 8 times, it is easy if we calculate our P inverse P, and then by using diagonalization concept, we can easily calculate our A power 8. Let's move on to the problem. Solution. To find P, first we have to find the eigenvalue and eigenvectors. So, in order to find the eigenvalue, first the characteristic equation of the given matrix we have to calculate is nothing but modulus of A minus lambda I equal to 0. That is, modulus value on taking our diagonal elements as minus lambda, we have that is equal to 0. On calculating the modulus value, we just have lambda plus 1 into lambda minus 3, lambda minus 4 equal to 0. On solving this and finding the lambda, we have lambda 1 is equal to minus 1, lambda 2 equal to 3 and equal to 4 or the eigenvalues of the given matrix A. As it is a 3 by 3 matrix, we have 3 eigenvalues. All the 3 eigenvalues are distinct here. For this problem, we have distinct eigenvalues. And next, we have to calculate the eigenvectors corresponding to each eigenvalue of the lambda. Okay, first let x is equal to x1, x2, x3 whole power transpose corresponding to the eigenvalue. It can be given by using the equation A minus lambda into x equal to 0. First, for lambda equal to minus 1, we are going to calculate the eigenvector. So, by putting lambda equal to minus 1, we have A minus lambda I into x equal to 0. We have the given matrix our A as 1, 2, 3. Now we are subtracting our lambda, so it becomes 2 here. On subtracting the lambda value in the diagonal matrix, the diagonal elements, we just have A minus lambda I this thing, that into x equal to 0. On solving this matrix multiplication, 2 into x1 plus 6 into x2 plus 1 into x3 becomes the first equation, that is equal to 0. Then the second one, 1 into x1, 3 into x2 plus 0 into x3 equal to 0. Next 0 into x1, 0 into x2 plus 4 into x3 equal to 0. So, we have 3 different equations. On solving any 2 equations, all the 3 are indifferent. So, we can choose any 2. By choosing any 2 equation and we have solving this, we have the value for x1, x2, x3, which is nothing but here x3 equal to 0. By x3 equal to 0, we substitute in first equation, we have x1 is equal to minus 3x2. By taking any one value, by taking x2 equal to 1, then we have x1 as minus 3. Thus, we have the eigenvectors of first one or lambda equal to 1 is minus 3, 1, 0. For corresponding to lambda equal to minus 1, we have calculated. In the same way, we have to calculate it for lambda equal to 3 and lambda equal to 4. Okay, this for lambda equal to 3, the same way A minus lambda into x equal to 0, we have to subtract the diagonal elements by using minus 3 and getting that A minus lambda is equal to this thing, that into x equal to 0. On product, we just have 3 equations. Here all the 3 elements are 0 in the last column, the last row, So we have only two equations. On solving these two equations, we have the eigenvector as 1, 1 minus 4. In the same way, we have to calculate for lambda equal to 4. For lambda equal to 4, the eigenvector is calculated as a minus lambda into x equal to 0, in which we have three different equations. On solving these three equations, we have x1 equal to 2 and x2 equal to 1 and x3 equal to 0. Thus, the eigenvector corresponding to lambda equal to 4 is given by 2, 1, 0. Thus, let us calculate the P. Let P be the matrix whose column elements are nothing but the eigenvectors of the given matrix A. Thus, our P is nothing but 3, 1, 0, 1, 1 minus 4, 2, 1, 0. The elements of this can be noted as, the first one is called as an A11th element. Second is nothing but first row, second column, so A12. First row, third, which is nothing but A13. In the same way, we are just naming this P, where P is called the model matrix, because this P can go into transfer our A into D. That's why our P is called as a model matrix. We have to calculate P inverse. The definition for the inverse is nothing but 1 by modulus of P into adjoint of P. If we need an inverse matrix, then we have to find the modulus matrix of the given one and the adjoint of that given matrix. First, we calculate the adjoint matrix. The definition. For adjoint P, we have to calculate the cofactors of each and every element. So, first for A11, we have A11 means we have to reduce that first row and first column and solving the remaining as a modulus. So, A22, A33 minus A23 into A32. On solving these things, we have answer as 4. Next, we have to calculate for the element A12. For A12 means we have to leave the first row and the second column and taking the modulus for the remaining, which is nothing but A21 and A33 minus A23 and A31. On calculating the value corresponding here, we have answer as 0. Same way A13. For all, we have to calculate for A11, 12, 13, 21, 22, 23, 31, 32, 33. For each and everything, we have to calculate the cofactors. So, finding the cofactors, similarly for A33 means we have to eliminate the third row and third column. On taking the remaining value as a modulus, we just find A11 into A22 minus A21 into A12 and finding the answer as a minus 4. By taking the cofactor matrix, we just have the adjoint matrix as that cofactor elements the whole part, which is nothing but on taking transverse means changing our column into row and row into column. So, we have the matrix as this thing. And also we have to calculate the modulus of the given matrix, this P. So, modulus of P, we have calculated. Modulus of P is nothing but minus 3 into 0. This is our P matrix. Thus, for this P, we are going to calculate the modulus value. So, modulus of P is nothing but minus 20. Thus, P inverse is nothing but 1 by modulus of P into adjoint of P. This is our P inverse. Next, we are going to calculate the diagonalization. Diagonalization D is nothing but P inverse A into P, which is that A, but 1 by minus 20 into this thing, that is P inverse value, A value and P value. Next, we have to multiply all the three. So, that first we have to multiply the first two matrix and we get the answer as this thing. Then, we have to multiply this matrix with the third one. So, we get the matrix as this thing. On dividing by 20, we just get a matrix as this thing, minus 1, 0, 0, 0, 3, 4, 0, 0, 4, where minus 1, 3 and 4 are nothing but the eigenvalue of the given matrix A. Thus, D is the diagonal matrix which contains the eigenvalue. Thus, our matrix A can be diagonalized. Yes. Next, we have to calculate the higher power, which is nothing but A power 8. To find A power 8, we know since P inverse AP is equal to D, in order to by simple calculation, we just know that A power 8 is nothing but P into D power 8 into P inverse. So, either P into, we have to multiply the matrix P into D power 8 matrix and then multiply this with P inverse matrix. We have P. So, calculated that P inverse A power 8 into P, which is nothing but P on raised to the power 8 minus 1 reduced to 1, 3 power 8 is nothing but 6561 and 4 power 8 is nothing but 65,536 and then multiplying with this. On multiplying all the three matrices, we just get the answer as A power 8 is equal to this much thing. So it is very much easy. Instead of calculating A into 8 times, by using the diagonals raised to the power, we can get the answer. Just in this problem, we just calculated our P and A power 8. Okay, next one more problem. For the first problem, we just calculated for 3 by 3 matrix. Next, I am taking just a matrix for a 2 by 2 matrix. Okay. Find the matrix B, which diagonal is the matrix A, E. Okay. And we have to verify whether our D is nothing but P inverse AP is a diagonal matrix. And also find A power minus 6. They are asking to calculate a P and verify that our D is diagonal. Two things. Third thing is we have to calculate our A into power minus 6. Okay. In order to calculate the eigenvalue and eigenvector, first we have to calculate the characteristic equation. The characteristic equation is given by modulus of A minus lambda I equal to 0. On solving this modulus value, we just get an answer for lambda as 2 and 5. Thus, 2 and 5 are the eigenvalues of the given matrix. Next, we have to calculate the eigenvector for lambdas, for each and every lambdas. That's for lambda equal to 2, we have to find the eigenvector. For lambda equal to 5, we have to find the eigenvector. Okay. To find the eigenvector, what is the equation? It is nothing but A minus lambda into x equal to 0. When lambda equal to 2, we have to substitute. Instead of lambda equal to 2, we just gave a matrix A minus lambda I as 2, 1, 2, 1 into x1, x2, that is equal to 0. On solving this, we just get a single equation, which is nothing but 2x1 plus x2 equal to 0. By substituting x1 equal to 1, we have x2 equal to 2. Thus, we have the eigenvectors as 1 and minus 2 for lambda equal to 2. In the same way, similarly, we have to calculate the eigenvector for lambda equal to 5. For lambda equal to 5, the corresponding eigenvector is given by A minus lambda into x equal to 0. On same thing, A minus lambda I matrix becomes this thing, that into x1, x2 equal to 0. On solving this equation, we just get the two equations. More or less, they both are same. By substituting x1 is equal to 1, we just get x2 equal to 2. So, we get the second eigenvector as 1 and 1. Next, we have to calculate the model matrix. Model matrix P is nothing but the column elements contains the eigenvectors of the given matrix A. So, 1 minus 2, 1 and 1, which is nothing but this is our P. Next, we have to calculate this P belongs to our diagonalization method or not. So, in order to find P inverse AP becomes a diagonal, we have to calculate the P inverse, where P inverse is nothing but 1 by 3 into, which is nothing but P inverse is equal to 1 by modulus of P into adjoint of A. So, P inverse is nothing but modulus. Modulus of P is nothing but 1 by 3. Adjoint matrix is nothing but on taking this value and taking the symbol as a negative. We have to change the diagonal elements and we have to change the symbol in this column. So, we just get the answer as 1, 2, minus 1 and 1 directly. Then we have to calculate P inverse into A into P. Next, 1 by P. P inverse is nothing but this value. A is nothing but the given matrix. P is nothing but this thing. We have the P. So, we have to multiply all the three matrices. By multiplying first two matrices, we just get an answer as this thing. Then this one with the second one, we have to multiply in both. We have an answer as this thing. On dividing by 3, we get an answer as 2005, which is nothing but the diagonal matrix, in which having the diagonal elements are nothing but the eigenvalues of the given matrix. Thus, the D is nothing but the diagonal matrix containing eigenvalues. Therefore, A can be diagonalized. We have proved two things. What they are asking? They are asking three sections. First one, we have to calculate P. Next, we have to find whether the P inverse AP is diagonal or not. Yes, both we have solved. Last thing, we have to find the value of A power 6. So, A power 6 is nothing but, in order to, by using the diagonalization concept, we are finding A power 6. A power 6 is nothing but P into D power 6 into P power minus 1. So, this is our P value, this is our D power 6 value, this is our P inverse value. On multiplying all the three matrices and divided by 3, we get the answer as A power 6 is nothing but 10438 and this thing. So, thus, by using the diagonalization concept, we calculated our higher power A power 6 in the easiest way. Next, for both the problem, for both our example 1 and 2, we take the distinct eigenvalues. Now, I am considering repeated eigenvalues. In case if our matrix, given matrix contains a repeated means, what we are doing? Let's go. Let's first one, diagonalization the matrix of A is equal to this thing. They have given a matrix A and they are asking to diagonalize the given matrix. Yes, step 1. In order to find the eigenvalue and eigenvector, first thing we have to calculate the characteristic equation. In order to find the characteristic equation, we have to find the modulus of a minus lambda I equal to 0. So by subtracting lambda in the diagonal elements, we have the matrix as this thing. On solving the modulus value, we have the equation as this thing. By solving lambda equal to 3, that's a cubic equation. We have 3 roots, which is nothing but 1, 1, 5. We have 3 roots. On solving by synthetic division, we can find the roots of this given equation. The roots are nothing but 1, 1 and 5, in which the eigenvalues are repeated 1, 1. Okay. Next, to find the eigenvector corresponding to 1, 1 and 5. First, we calculate the eigenvector for non-repeated value, which is nothing but 5. To find the eigenvector, we have to solve the equation a minus lambda I into x equal to 0. Thus, for lambda equal to 5, first I am finding. Putting lambda equal to 5 in the column, in the diagonal elements, and we have that a minus lambda into x is equal to this thing. See, by putting lambda equal to 5, we are finding one matrix, that matrix into x1, x2, x3, just having 3 equations, which is nothing but these 3 equations equal to 0. In order to find this thing, we have to solve any 2 equations. Therefore, from equation 2 and 3 or 3 and 4, anything, all the equations are in a different manner. So we can choose any 2 equations and solve for x1, x2, x3. We have the answer as, by using the division rule, we have the answer as x1 by 1, x2 by 1, x3 by 1. Which is nothing but 4. Since by ratios we just calculated divided by 4, we have 1, 1 and 1. Thus, the eigenvector corresponding to lambda equal to 5 is calculated as 1, 1 and 1. One more thing. Then we have to calculate for lambda equal to 1. In the same way, by putting lambda equal to 1 in equation 1, thus in the value of this thing, by putting lambda equal to 1 in equation 1, we have again 3 equations, which is nothing but all the 3 are in the same. So by considering any one equation, taking one equation in which we have say that x2 equal to 0 in equation this, then we have x1 plus x3 equal to 0, or x1 is equal to minus x3. Taking by x3 as an arbitrary non-zero real number, say 1, we have the answer as x1 to be 0, but an eigenvector is a non-zero vector, so x1 is equal to minus 1. By choosing our x3 equal to 1, we have x1 is equal to minus 1. Therefore, for lambda equal to 1, we have the eigenvector x2 is nothing but minus 1, 0 and plus 1. No need, we have to calculate a non-zero eigenvectors. All the 3 elements in the eigenvectors need not be 0. In order that we just calculate it. Again for lambda equal to 1, we have to choose. Now choose either x1 equal to 0 or x3 equal to 0. In first case, we considered x2 equal to 0. Now I am considering x1 or x3 equal to 0. Suppose let us take our x3 is 0. Then we had the equation as this way. By taking x2 equal to 1, we have x1 is equal to minus 2. Thus our x3, the third eigenvector as minus 2, 1 and 0. Therefore, 5, 1, 1 are the eigenvalues, and the corresponding eigenvectors for these eigenvalues are nothing but x1 as this thing, x2 is this thing and x3 is this thing, or the corresponding eigenvectors of the given matrix A. Next we have to find the model matrix. For calculating P, model matrix is nothing but the elements, column of the elements contain the eigenvectors of the given matrix. So P is nothing but first one, it belongs to first eigenvector, second belongs to second eigenvector, third one belongs to third eigenvectors. So then we have to calculate P inverse. P inverse is nothing but 1 by modulus of P into adjoint of P. Same thing as from problem number 1, we just finding P inverse as this thing. First we have to find 1 by modulus of P separately. For this P we have to take the modulus value. Then for each and every element we have to calculate the cofactors. Thus the adjoint matrix is nothing but this thing. Thus P inverse is equal to this thing. Now I am calculating P inverse into AP. This is P inverse A into P. On multiplying the 3 matrices, we just have answer as this thing, which is nothing but the diagonal matrix having the diagonal elements as the eigenvectors. Thus we have a diagonalized A. It means the given matrix A, even though it have a repeated roots, we have diagonalized form of the A. So these are the 3 examples. what we have studied in this chapter. Here we are diagonalize the matrix by using similar transformation. It means P inverse AP is equal to D. These are some of the practice problem for you for reference. Here first one is equal to the minus 1 etc. All the three I have given here are nothing but in a 3 by 3 matrix. Since 2 by 2 matrix is very simple, I am just giving you a 3 by 3. First calculate the eigenvalue, next find the eigenvector, then find the model matrix P, then find P inverse A into P, calculate whether it becomes the diagonal matrix having the diagonal elements as the eigenvalue of A. Check and find out whether the given matrix are diagonalizable or not. Okay. In this section, we calculated the diagonalization by using similar transformation. In our next video, we are going to calculate the same diagonalization by using orthogonal transformation. For orthogonal transformation, it will be simple. Simple or it might be differ from the similar. By using similar transformation, we are calculating in the easiest way. By orthogonal transformation, we have to check. So, what is the difference between the similar transformation and orthogonal transformation? I will just tell all those things in our next video. Okay? Yes.